Hi there. Welcome to another episode of Q&A about history of science and technology. I'm happy to try and talk about both things that I've been involved in myself and things I might have studied. I have to say I'm in the middle of a kind of a difficult history project right now that I thought was going to be a really easy history project. It's soon going to be the 20th anniversary of my big book, A New Kind of Science. The publication of that book on May 14th, 2022 will be the 20th anniversary of the original publication of that book. And I thought it would be interesting to go and write a little bit about almost the anecdotes associated with the making of that book. I thought this was going to be easy because I thought, heck, this was something I did myself starting about 30 years ago in 1991. It's turned out to be a lot harder than I thought. And it kind of reminds one of the following fact, that when one lives through events and does things, one is not forming the thoughts at that time of what the kind of arc of history that connects those events will be. And so there are things where I did this, I did this, I did this, but then if you look at it zoomed out a bit, you can kind of see, well, that's what led to this or that happening. But I hadn't really formed the thoughts that that's how things sort of were strung together back when I was just doing them, so to speak. So I've been trying to reconstruct, for example, how it was that I went from, in 1991, the idea that I would write a small book that would be kind of an exposition and condensation of work that I'd done mostly in the 1980s, mostly towards answering the question sort of, how does there come to be complexity in nature? How did I go from that to writing the 1,280-page book that is A New Kind of Science that really has a much bigger kind of story than this original question about sort of the origins of complexity, which I think it manages to handily dispatch that question and then goes on to the much broader kinds of issues that eventually gave the book the title A New Kind of Science. So in any case, I've been trying to trace down all of those things, and a lot of that has also turned out to be a lot of elaborate history of technology that sort of was very entangled with what made it possible to produce the New Kind of Science book. In the end, things even to do with printing technology and the possibility of making very high resolution images of things like cellular automata with sort of where every pixel counts and so on, and having that be crisp, that required all kinds of printing technology issues that I was also way too deeply involved in around 2001 and 2002. Anyway, it's something I've been trying to write, and it's also required going back and have most of the material, just to give some sense of sort of history on the ground. I have kind of the final files that were used for producing the book. I even have a virtual machine that is the actual book production software as of 2002, all preserved and able to be run as a virtual machine, some kind of Windows machine, brought back to life with very cruddy looking UX, I have to say. Then I have files, and I have mostly the latest versions of all the files that were used to create the book and all the programs that were used to create the book. Earlier versions are on tapes, and those tapes we still have, and we've been restoring some of those tapes. A little bit of a challenge to find a tape drive that will read 8mm videotape. That was what was used as backup, a backup medium. And it's a little confusing, and the tapes were not as well labeled as they should have been back 30 years ago. But we've been slowly restoring some of those tapes and able to see files. And they're just all kinds of remarkable things that I find. One of the things that's very striking to me, looking, for example, at email that I sent 30 years ago, I have that all archived back to 1989, actually. I have all my sent and received email archived. Okay, there's some footnotes to that, like I was using a Next computer, which had a very beautiful attachments mechanism for email, but unfortunately the archiver decided to get rid of the attachments because on the grounds that they were too big and bulky and so on. And so those attachments have to be hunted down separately. But the the thing that is sort of remarkable about reading email that one wrote 30 years ago is, I feel pretty satisfied that the things I wrote were quite sensible. But every story that one is describing and being part of in those emails is pretty much the end of the story is now known 30 years later. There are all kinds of interactions with people and interactions with organizations and so on, and one kind of knows the end of those stories. And that's been quite interesting to me to try and sort of understand the more of the arc of what's happened there. I think an awful lot of the emails were to do with building our products and things and building Wolfram language and all that kind of thing. And it is very satisfying to see that there were, particular bricks being put into the cathedral, so to speak, back in 1991. And yep, that brick is still there, and it's still holding up some piece of what's been built on top of it. So that's a nice thing to realize, that one wasn't wasting one's time and just building a structure that all got torn down in the intervening years. No, those are bricks that are part of a large structure that got built up. But in any case, that's been, I was going to say about other raw material. There's the online, the archives of email and archives of files, backup tapes. I also have physical pieces of paper that I wrote things on and printouts and so on, at least from 1993 onward. Those have not been scanned, and those are and that's a thing that I'm about to start looking through. It's kind of an interesting archaeological exercise, because in order to kind of define I knew that I was making sort of archaeological layers. In order to make sure I had date markers in there, I would throw in things like the phone list from our company, or random pieces of material that were dated in one way or another. And so that's kind of a place where one gets to see sort of things of the time embedded in all kinds of notes and so on. Many of those notes are almost timeless, that, whatever they might be printouts of pictures of Turing machines or something like this. And those would look, well, they would look better today just because they're high resolution, but not necessarily anything else. So the thing that, trying to go through those things, it's, I was going to say, another thing that I've been finding is photographs. And there are photographs that were both taken for the construction of the book itself, and there are lots that didn't make it into the final book. There are lots of strange photographs of all kinds of things that were intended as examples of complexity in nature. Things like this didn't make the cut into the final book. Those are interesting to see. They're mostly black and white photographs. Mostly what's in my archives is the contact sheets from the negatives, just printed directly as little 1-inch square things, or whatever, 1-inch across things. It is a little frustrating that, whereas in modern times, when all sort of photography is, or in practice is digital, and one can, one has lots and lots of pictures and one can go find them, there are things that I really want to find from 1991 that I know there are pictures of. I just can't find them. And it's sort of because I didn't have an organized archiving scheme for photographs. I didn't take that many photographs. And when I did, they were just, negatives and little folders of little, printed photographs, so to speak. So anyway, I'm still searching for some of those things, hoping to find them for my making of NKS, my essay about that. Let's see. Questions here. Oh, there's a pretty technical one here from Parmenides about the history of dimensional regularization and Zeta regularization. How are they related to renormalization? Okay, well, I'll try and address this a little bit. It's one of the awkward things in physics is, if we think an electron is a kind of a geometrical point, there are lots of things that one might compute about it that are infinite. It's of zero size, but that means that, for example, its electric potential, its 1/r type potential, is infinite right at the electron itself. And you might say, oh, that problem is going to go away when you do quantum mechanics and quantum electrodynamics and so on, but it doesn't go away. There are still infinities when you do the integrals and things to compute, for example, the self-energy of an electron. How much, what the energy associated with an electron basically having electromagnetic interactions, emitting and reabsorbing virtual photons to itself. If the electron is of zero size, then those integrals diverge. Those integrals are usually given in momentum space, so you're doing an integral over all momenta of some particular quantity, and that integral has divergences in it. But those divergences have the property that they only diverge in four-dimensional space. They diverge, but if you are in let's see, lower dimensional space, they do not diverge. And so what you can do is say, well, imagine I was in four-dimensional space. Well, no, actually, let me be in 4 minus epsilon dimensional space. And let me do the integrals in 4 minus epsilon dimensional space instead of four-dimensional space. And then I can compute them and they're finite, and I'll get some results which are functions of epsilon. So they might have a term 1 over epsilon squared plus 1 over epsilon plus 3 plus something else. And then so when epsilon goes to 0, corresponding to exact four-dimensional space, those terms that are like 1 over epsilon squared terms and so on go to infinity. But if you've got several different things that you're looking at where they've all got a 1 over epsilon squared term, you can often, and this is sort of the trick of renormalization, you can often cancel the 1 over epsilon squared terms and just look at the finite pieces that get left over, and that gives you the actual values that are relevant for doing experiments and so on. So kind of the idea is, let's just sort of modify the effective dimension of space, do the computations, which will then be finite, but depend on the deviation of the dimension of space from 4, cancel out those terms, which are now terms we can sort of just pick up and handle algebraically and look at what the differences are. Now, when I say that one's doing these things assuming a different number of dimensions of space, it's a very weak version of doing that. It's basically just using the fact that we know the volume of a sphere in d-dimensional space, and it's given by something that's proportional to r to the d times some product of gamma functions and things, which for a circle it's pi r squared, for a sphere it's 4/3 pi r cubed, for a hypersphere it's what is it? It's 4 pi squared times r to the 4th, something like that, for a four-dimensional hypersphere, and so on. And it keeps going in different dimensions. But that formula can be analytically continued to an arbitrary d-dimensional sphere. And that's essentially what one's using in doing these calculations in particle physics and quantum electrodynamics and so on with dimensional regularization. Now, I think the first place where I know that dimensional regularization was used was a little report called Diagrammer that was written by Tini Veltman and Gerhard 't Hooft back in 1976, I would say, give or take. It was a CERN report that was trying to describe how to do Feynman diagram calculations, and it was sort of I think that was the place where I certainly first saw dimensional regularization being used. It became more important to have sort of streamlined Feynman diagram calculating techniques when one was doing them for QCD. For QED, quantum electrodynamics, there had been particular things that were computed, the anomalous magnetic moment of the electron, the various other kinds of scattering processes and so on. But those had pretty much been computed by the 1940s, 1950s, 1960s. The main experimentally accessible versions of those have been computed, with the exception of the anomalous magnetic moment of the electron, anomalous magnetic moment of the muon, which was a very high precision computation, which went on being computed higher and higher precision. And that was sort of a specialized activity for a number of years. But kind of the general, how do you roughly compute Feynman diagrams? The main Feynman diagrams that people have been interested in quantum electrodynamics have been computed by the 60s and so on. But then quantum chromodynamics came along, the theory of quarks and gluons, and there's a whole raft of new Feynman diagrams to be computed. There are also Feynman diagrams to be computed in what's now called the standard model, used to be called the Weinberg-Salam model, the model in which there are W bosons and Z bosons, gauge bosons, in addition to the photon. There were computations to be done there. And there were also some toy field theories like phi-4 field theory, phi-cube field theory, where people did some Feynman diagram computations. But so by the late 70s, there was a need, mid to late 70s, there was a need for sort of more streamlined Feynman diagram computing techniques, and dimensional regularization was the thing that came out of that. The importance of dimensional regularization is more a physics point, is that people have been using things like explicit cutoffs, where you say integrate the momenta up to some value of the momentum. Doing that broke relativistic invariance, and so caused one to have all kinds of fancy footwork associated with making sure that the results one got would be relativistically invariant. Dimensional regularization didn't have that problem. And so that was how that originated. I myself used it quite a bit. I was quite an enthusiast of it in the, when was that? 1978-ish timeframe. Actually, one of the things that I had figured out, which a student who was working with me subsequently wrote up, but I had been interested in, okay, so we know about the volume of a whole sphere. How do we think about how do we think about kind of angular dependence in d-dimensional space? And things called Gegenbauer polynomials, which are generalizations of the spherical harmonics. Spherical harmonics are the things that give you, those nice orbitals and so on in chemistry. They're the three-dimensional, well, in two dimensions, their sines and cosines are the sort of orthogonal functions on intervals. In three dimensions, the analogous sort of orthogonal functions on the sphere are the spherical harmonics that give you orbitals in chemistry. The question is, what's the d-dimensional generalization of that? And the answer is Gegenbauer polynomials. And so it's possible to decompose a bunch of the kinds of things that appear in Feynman diagrams in d dimensions into Gegenbauer polynomials. And there's a whole nice theory of that that I started working out, and a student who worked with me ended up, this is back in probably 1979, 1980-ish timeframe, ended up finishing and writing up. And I think that's become quite an industry in the years since. But that's a little bit on the theory of dimensional regularization. In recent times in our physics project, we're interested in these hypergraphs that represent the low-level structure of space and whose limit can correspond to sort of ordinary space in d dimensions, where d is not necessarily determined to be, certainly not 3 and not even an integer. And so it's of interest to understand how things work in space that isn't integer dimensional, but that's actually quite complicated and much more difficult than the case of dimensional regularization, which is mostly these volumes of spheres or sort of easy angular dependence in spheres that shows up. Let's see. There's a question here from Erin about when and how was the first compiler made? What language was it for? What language was it written in? If I know that history correctly, the first compilers were for Fortran and then COBOL, and they were written around 1958, I think. The Fortran, the name, stood for formula translation. And what had been done previously is when you programmed a computer, you were using the machine code of the computer, and you were telling the computer to, sort of open, turn this gate this way, do this thing with this accumulator. You were really telling it step by step in its terms, do things with this particular piece of the computer's hardware. And that was how you did a computation. Kind of the idea, and this was an idea I think IBM was much involved with, the idea of formula translation, where you would write down something that looked like a mathematical formula, and it will be translated into that set of operations that say, send data from this from this accumulator to that register and do this operation on it and so on. It was a way of translating something that looked like a formula into those machine code operations. And that was kind of the origination of Fortran. Now, I assume that the Fortran compiler was written in machine code. There was some, let's see, there was a thing called autocode, I think, at the time, that was a similar kind of idea. There were a variety of kinds of approaches. I mean, that came in around the same time of kind of how would you translate some high-level description into machine code. The thing that is sort of shocking is that some of the operations like loops and so on and conditionals, all those kinds of things really didn't change from then until now. From the very beginning, the dawn of kind of electronic computing in the 1950s, late 1950s, to today, most programming languages still work in terms of loops and variables and arrays and so on, very much the same as those very first languages used. I think our own Wolfram language system is one of the very few exceptions. I mean, our objectives are much broader than sort of the pure programming objective, but the notion that one can sort of think about computation not in terms of variables and loops and so on, and it's been sort of bizarre, this kind of accident of history, that the very first computers had their very first compilers that worked that way, and it's been sort of translated ever since. Now, the first time when people started to try and make a more formal description of kind of the language that computers were programmed in, I think was ALGOL. Oh gosh, when was the first ALGOL specification? I think 1960 maybe, ALGOL 60, if I remember right. And so ALGOL, the idea was that this would be a sort of precisely mathematically defined language that was going to be used to program computers. And it made use of this thing called Backus-Naur form that had been invented around 1956, I think. That was this kind of recursive definition of a language that says, you know, a possible expression in the language can be an expression plus an expression, or it can be open paren, expression, closed paren. This kind of recursive description of a language that could be given, and that was kind of the origination of sort of what became the specification for ALGOL. Now, very curiously, right around the same time as Backus and Naur making that up, around 1956, Noam Chomsky was inventing kind of generative grammars that have been, I think, somehow, there was a person called Zelig Harris who was also involved in kind of the sort of notion of formalization of languages and formalization of description of languages. And I have been very curious how these things landed both at the same year, so to speak. This sort of approach to making specifications of computer languages and approach to making a description of human languages. And I asked Noam Chomsky this question once. I didn't get a terribly useful answer. I think, and I actually recently asked somebody else who gave me a little bit more of an answer to that question. But I'm not quite sure which came first or whether it was sort of a convergent evolution kind of thing. But in 1956, both of these things kind of landed. Now, people go back and say, actually, there were descriptions from much longer ago that looked like this. I mean, when the typical grammar book and grammar books that existed since antiquity, there were Latin and Greek grammar books, certainly Latin grammar books from Roman times. But those grammar books tend to be set up in a little bit of a different way, although they definitely have sort of tables of what you can do, so to speak, but not so much this kind of recursive description of a sentence is of this and a phrase is of that, and so on, recursively going down. People have often said that Panini, who was a grammarian of Sanskrit, from around, well, a couple of thousand years ago now, possibly longer than that. It's not very easy to date. That he had sort of I don't know whether one knows it's a he, but that person had a description of the grammar of Sanskrit in this sort of recursive form. I did look at the actual originals of that recently, and it's pretty hard to understand. Obviously, it's not written in, I can't read Sanskrit, and it was originally written in Sanskrit, so I'm looking at a translation, which already is difficult, but it feels more like kind of aphorisms that just say things like, you know, a sentence has a verb in the middle. They don't say things as abstract as that. They're a little bit more example based. So it's pretty hard to tell sort of exactly how that history connects. But anyway, Algol 60, I think, developed the sort of formal description. And I'm afraid, as has happened a few times in the history of computing, it was a big committee that invented this whole Algol specification. And I'm sure that people were adding all these pieces about, yes, we should have this functionality and that functionality. And in the end, it wasn't really implemented completely. And I remember when I first used a computer in 1973 or so, there was supposedly a sort of Algol-like language. It was called Simpol, which was a simple version of Algol that was more or less completely supported on that computer. But Algol was like still way in the stratosphere of something way too complicated to actually support. So I think that's a little bit of the history of those things. Now, the concept of writing a compiler for a language in the language itself was something which was certainly somewhat understood, I would say, well, certainly by the 70s. The actual doing of that, probably, I wonder what the first compilers that were written in the language itself actually were. Probably the compiler for C, which must have been 1976-ish time frame, 7 maybe. I suspect that was written in C. The original compiler for that, as part of the C language, was developed by Ken Thompson, Dennis Ritchie at Bell Labs. I knew those people back in the day. That was developed originally for the Unix operating system, which was being developed at Bell Labs for, among other things, telephone switching applications. I mean, Dennis Ritchie actually had written his thesis, I think, about things called register machines, which are a simple model of computation. And it's kind of a little charming, and I've never really traced it through completely, the extent to which the very lovely minimal sort of syntax of C derives from the actual sort of formal description of register machines. I mean, C as a language, sort of a derivative of BCPL. There had been a language called B also, and that was, C was sort of the next in line in the things that are derived from that. Let's see. Well, Aaron is asking about the history of computer graphics standards and libraries, such as OpenGL and so on. Well, I know some of this. I'm not sure I know it completely. The first computer graphics things, okay, back in the day, oscilloscopes were basically the output for graphical kinds of things. And you would have, you know, the dot on a cathode ray tube, and you would sort of make the dot dance around. And there were so-called storage scopes, which had phosphors that had very long decay times. So the spot would run around on the screen, and you could sort of draw something by having that spot by sort of keeping the where the spot had been. And I think things like the PDP-1 had those kinds of displays. That must have been 1961, 2, something like that, had those kinds of displays. And early, both early air defense computer was based on those kinds of things, I think, and its display was based that way. I think some air traffic kinds of things worked that way. Very first, the Space War computer game, I think, worked that way. So those were sort of very early computer graphics where you just, and a storage scope. Now, when I started using computers and making graphical things with computers, there were basically two technologies. One was essentially storage scopes, a little bit generalized by that time. Company Tektronix had made terminals that also had this kind of graphical character to them that was kind of like oscilloscopes, and they would typically, you'd be able to print from that, print from the display by using essentially a photographic printing process. You'd have the display and you'd press a button and there'd be this sort of a photographic-like paper that came out that had kind of an image of what was on that display. That was technology number one, was kind of the cathode ray tube oscilloscope type technology. Technology number two was pen plotters. And I, for example, used, this must have been 1976, I used a pen plotter that was HP, had a very nice desktop calculator / computer, used a kind of a version of the basic programming language, and it had a pen plotter. And so a pen plotter, you're moving sort of X and Y directions and moving the pen around. And I think it had, it even had several different pens, so you could make plots with different colors and so on. So those were two of the early technologies people used. Now, subsequently, this notion of a bitmap display, that is a display where there is a piece of memory that stores values in it, and where there is a display that is kind of a copy of what's in memory, so that you can get this whole raster of data on the display. That's something that I think probably existed by the early 70s at the latest. I think the first time I saw one of those was probably at Xerox PARC, the Xerox Palo Alto Research Center, probably around 1979, perhaps a little earlier than that. No, it must have been 1979, I think, where there was both displays that were bitmap displays and that were I should have explained. Yeah, I mean, in early, let's see, I'm now the early computers like the Atari and the Apple II and things like that. They had a display where you could specify the pixels on the screen, but they were pretty low resolution. The things at Xerox PARC, for example, were very high resolution, high enough resolution that you could form letters, for example, by just the dots in the letter being directly rendered to the screen. Before that, in cathode ray tubes, there were so-called character generators, which were separate kinds of things, where, for example, you would physically have the electron beam go through a metal kind of template, a metal thing that would make kind of a silhouette of the beam to produce those letters, rather than having it be that the letters were formed by actually constructed sort of pixel by pixel on the screen. That was kind of the new thing there. I remember actually back when I first visited Xerox PARC, there was also a color laser printer, which was also a completely, a technology that didn't really reappear elsewhere for quite a while. But then, in terms of computer graphics, and I may have my dates slightly scrambled, Evans and Sutherland was a company based in Utah that was an early computer graphics company that invented quite a lot of the methods for rendering 3D objects and so on. I'm trying to remember all these pieces of history because there are lots of individual parts. There was a company called ascii, Information International Incorporated, based in Los Angeles, that had been started, co-founded by a friend of mine named Ed Fredkin. and that was founded in the early beginning of the 1960s, did lots of different things, including sort of producing some very early computer graphics for example, television productions. I think they produced the CBS spinning logo as a computer simulated thing. But there have been pieces like that. There's so many different parts to all of this. But I think the way that that sort of some of the modern graphics standards emerged, I don't know completely the lineage of this, but somehow out of Evans and Sutherland came various companies, including Silicon Graphics, which was a company that made very beautiful purple computers and things. That was back in the mid to late 1980s. And SGI, Silicon Graphics, one of its specialties was having it be the case that you could take a 3D geometry and have it rendered on the computer and spin it around and do all those kinds of cool things. And it had special purpose circuitry that allowed you to do those kinds of things. And I think gradually that sort of special purpose circuitry methodology gave way to these libraries like GL. I'm not sure, there were a couple of companies, there was one called Ardent and one called Stellar, which were sort of mini supercomputer-ish companies that came into existence right around the time Mathematica was first released in 1988. Those companies were very much, those two companies were very much duking it out in the kind of small graphics-oriented supercomputer-ish type machines. Strangely, they were eventually merged into a merged company called Stardent that was Stellar and Ardent put together. But I think some of these graphics standards were developed by those guys as well. It sort of gradually went from, oh, you need all the special purpose hardware, as has happened throughout the history of computing, to, well, actually, with slightly better algorithms and so on, and faster general computers, you can just use generic CPUs to do all the computations. One of the things that's confusing is that back in the 80s, for example, people were producing all the time, we're producing these kind of special purpose coprocessors where it's like you've got your CPU, but then you also need the FPU, that's the floating point unit, or you also need the special arbitrary precision arithmetic floating point unit, or you need the special thing that does this or that kind of operation. And the typical experience was that by the time you really got those things up and running, CPUs, because of the greater economic pressure on just make generic computing faster, had gotten to the point where with a bit of clever algorithm work, you could sort of outperform the special purpose devices with the general purpose ones. And so for many of those things, for a while, we were supporting a variety of kind of special purpose coprocessor devices in early versions of Mathematica and so on. And then eventually we got kind of cynical about it, because it's like every time we go to all the effort to do this, a year later, oh, there's just a library that's a pure software library that does the same kind of thing. And there wasn't even any reason to go to all the work to support all the drivers and things like that. I kind of suspected the same thing would happen with GPUs, but it hasn't, and it probably won't at this point. That sort of everything that was a GPU functionality would kind of fall back into what a CPU could do and what compilers could handle generating code for. But that isn't what's actually happened. And I think the modern GPUs, which are much more vectorizing oriented things than they are specifically the kind of graphics processing world, but they were used for that. And that's kind of, again, sort of things are hardwareizing. Well, it's more complicated because there are libraries that make use of GPUs and so on, that make use of special hardware, but their interface is a pure software interface. I should say that sort of what enabled computer graphics really was the development of numerical linear algebra, which was something that really happened in the 1960s and so on. People had been thinking, how do you find the inverse of a matrix? Well, people knew how to do it by hand. It started to be relevant to know how to do it on computers by the beginning of the 1960s. And there was sort of slow development of, there are these different techniques which were crazy if you were going to do them by hand, but were really good if you were doing them systematically on a computer. Various kinds of decomposition of matrices that made it easier to invert them, those kinds of things. And sort of it became clear that, for example, the obvious way to multiply two matrices together, which takes, order n cubed time to work out the product of the matrices, there's a lot of sort of repeated operations that get done there, and you can gradually speed that up. That isn't, and gradually there are sort of different algorithmic techniques. Some of those algorithmic techniques end up being a bit infeasible for even matrices that are thousands of rows and columns and so on, or even up to millions of rows and columns. They're theoretically interesting, but not yet in practice interesting. But the development of numerical linear algebra, which got more and more standardized and more kind of burnt into at least very low-level libraries, was part of what enabled the possibility of computer graphics, and particularly 3D rendered graphics and so on. I mean, back when we were first developing Mathematica, Wolfram language, well, okay, so we had in SMP, the system that I developed from 1979 to about 1982, 83-ish, we had 3D graphics, and those were produced. How were they produced? In the end, they were rendered on things like these Tektronix devices. And did they have hidden surface removal? Hidden surface removal is the big thing. That is, you draw a surface and there are parts that in a real surface, a physical sort of solid surface, you can't see through. You can make a wire mesh, or you just make a meshed surface and you're just drawing the grid lines, and that you can make rather easily. And that's because you just need to know the coordinates of all those things. You need to do the perspective transformations and so on, but you can easily draw that. But it's much more difficult when you want to do hidden surface elimination. Actually, I think we did have that in SMP. I think it was done using a Z-buffer technique, where you basically say, let's draw out every piece of every line. Let's draw it at a particular XYZ pixel position, and you're just going back from the frontwards from the back, just saying which pixels can you see. When we built this for Wolfram language and Mathematica, starting in '87, we wanted to do resolution-independent hidden surface removal, hidden surface elimination, and that was much harder because we were using, as our graphics description language, we were using PostScript, which is a resolution-independent language for defining graphics, saying, you know, put this polygon here, put this line here, and so on. And we wanted to do that for 3D graphics, and that was much more challenging and required a much more algorithmic approach of figuring out, oh, this polygon that goes here obscures this part of that polygon here, and you know, when you have polygons in front of each other, they will often shatter the polygons behind them. You have to break them up into lots of pieces, and that was algorithmically quite tricky. Let's see, there's a question here from Word Nerd about the history of Wikipedia. How did it come to exist? I certainly don't know all the details of that. I remember going to an event. Oh gosh, when was this? This must have been 2002, 2003, at which somebody was showing off. Was it at MIT, and somebody was showing off sort of the Wikipedia thing, and it was something where they had a little thing that chirped every time an edit was made to the system, and it was chirping quite rarely actually. And the person who was showing me this was proudly showing that there was a page about me on Wikipedia, and asked me whether it was correct, and I think it was more or less correct with a few errors. And that person then went and edited the things that were wrong, and there was a chirp, and off it went. I think the subsequent history, well, I know from having talked to Jimmy Wales a long time ago, who was the sort of the person, the force behind Wikipedia. I know that our Math World website was one of the kind of inspirations for kind of the general sort of presentation of Wikipedia. And I'm afraid, well, then people sucked content out of Math World and put it on Wikipedia. Eric Weisstein, who's the person who originally created Math World, I had been trying to persuade him for a long time to accept sort of other people's contributions, and it was a challenge because Eric is a person with high standards, and most other people's contributions didn't quite meet his standards. So that was sort of a challenge: is how do you make this kind of group activity work and maintain standards and so on. I know Jimmy Wales originally had a project called Newpedia, which was an attempt to sort of make make an encyclopedia for the web. Let me go back to a little bit about other things that I know. So, you know, the whole world of encyclopedias had been started by people like D'Alembert in the 1700s in Paris, and then Encyclopedia Britannica was founded in Edinburgh. When was that? Sometime in the 1700s. And Encyclopedia Britannica had kind of defined, in the English language at least, this notion of what is an encyclopedia. And people had, you know, it had gradually grown. I mean, I certainly have a facsimile copy of the first edition, which is a small, you know, maybe 3-inch spine, 4-inch spine book that was kind of almost like an expanded dictionary of concepts and people and so on. And that was kind of the defining version of what an encyclopedia should be. The Encyclopedia Britannica gradually grew. I have a copy, for example, of the 1911 Encyclopedia Britannica, which is, so I don't know, well, a solid shelf of books. The 1911 one was particularly famous because it's one where the editors of the encyclopedia got lots of people like Einstein and so on to write articles about things, and it was very celebrity written encyclopedia, and it had a sort of it had quite a lot of long articles about things. I think maybe Einstein wrote the one about light, perhaps. But in any case, there was some sort of Encyclopedia Britannica developed as a business. It developed in a certain way, and it ran into all kinds of problems. I think it was sold for $1 at least twice in its existence. It somehow came into the orbit of the University of Chicago, and which I think owned it for a while. And through that, it came into the influence of a person called Mortimer Adler, who was a philosopher at the University of Chicago, who was a person who had sort of theories about the theory of knowledge and so on. And so he was quite influential in kind of I think he even became the editor of the Encyclopedia Britannica. And he eventually decided to sort of refactor how the encyclopedia worked into what he called the macropedia and the micropedia. The micropedia was kind of almost dictionary style, you know, quick hits on different topics. And the macropedia was sort of more essay-based kind of pieces. And I think he had a thing called the propedia, which was kind of an ontological, kind of a map of all knowledge. I remember looking at that document actually. Oh gosh, this takes me back. When I was working on SMP around 1980, I kind of had the idea of making kind of this kind of computational knowledge type system of having at that time sort of packages that would represent different kinds of human knowledge and so on, and represent those things computationally. And I remember getting out a copy of that Propedia kind of part of the Encyclopedia Britannica as a kind of an attempt to have a map of human knowledge, to kind of say what would be the categories of thing that we would need to implement. At that time, it didn't get implemented, had to wait for another, what was it, 30 years or so for the development of kind of Wolfram Alpha and our whole sort of computational language story. But there was a time that Encyclopedia Britannica had this sort of map of knowledge and had these kind of different levels that Mortimer Adler had defined for the encyclopedia. But meanwhile, Encyclopedia Britannica as a kind of as a business was kind of a funny thing, because it had been sold to schools and universities and things like that. But it also was sold to individuals and families and so on. And it had a very direct sales kind of approach. It had actual salespeople who would go out and try and sell you an encyclopedia. And sometimes it was sort of an interesting type of person who would become an encyclopedia salesman, because it was kind of a, you're selling knowledge in a sense. It's rather a nice thing, actually. I remember, years later, this is a strange footnote to history, but there was a very Californian kind of movement called EST, that was started by a chap who went by the name of Werner Erhard. It was, I think, EST something or other training, was the thing. It was kind of a self-improvement kind of, well, some people would call it self-improvement, some people would call it a cult. There was sort of disagreement about that. But anyway, this chap, Werner Erhard, took it upon himself, this must have been 1979, 1980, to start organizing conferences about theoretical physics. And I happened to be invited to one of these when I was quite young. And there's a smallish group of physicists, and another person who was there was Dick Feynman. And somehow the assembled group of physicists had kind of chosen Dick Feynman and myself to be the people who would, be the ones talking to Werner Erhard at this fancy dinner that was being had at this conference. And sort of at the time, of course, the web didn't exist, Wikipedia didn't exist. Knowing the history of Werner Erhard was not an easy thing to determine. And so I spent some early part of the dinner determining that, and I was very interested to find out that he'd been an encyclopedia salesman. And in fact, his kind of way of approaching sort of explaining the world and so on was very charmingly kind of, what you would do to explain fragments of knowledge to, at the time, I mean, in today's world, it sounds kind of silly because people say, oh, you want some fragment of knowledge? Well, just go look it up on the web. But back before the web, you want some fragment of knowledge, where would you find it? Well, you would find it in an encyclopedia. And that was a thing that people needed to be sold on, the idea that it was useful to have an encyclopedia. I have to say that when I first sort of was exposed to Encyclopedia Britannica, I looked up a few things that were relevant to science that I was doing, and I wasn't very impressed. And so for years afterwards, I kind of ignored the encyclopedia. And only many years later, when I I think the particular areas I had looked up had been particularly thin in the encyclopedia for whatever reason. But for some time, this must have been, late 80s, I just wanted to get myself a copy of the encyclopedia. And so I was like, okay, I got somebody to call and say, can we buy one? How much do they cost? And it's like, no, we'll send a salesperson around to tell you about it. It's like, no, we just want to buy it. And so I was at, this must have been in 1993-ish. I was finally at a book fair, a street book fair in Chicago. And there was an Encyclopedia Britannica booth. By the way, Encyclopedia Britannica was based in Chicago then as now. I thought, finally, there's a street booth where they are selling Encyclopedia Britannica. I can just buy one. And, I lived in the Chicago area at that time, put it in a box, take it home, I'm done. No more, let's send a salesperson out. And it was a huge challenge to actually buy the thing. It was like, look, I can write you a check. I can give you a credit card. I actually just want to buy it. How much does it cost? I think the answer was like maybe $1,500, something of that order. But the salesperson just wouldn't sort of let me escape and actually buy the thing without going into this huge song and dance and speech and so on and so on and so on, which was kind of interesting. But that was subsequently quite a business problem for the encyclopedia, because that direct sales model, which had a very elaborate commission structure and so on, didn't really survive the transition to electronic times. Actually, a friend of mine was a consultant for Encyclopedia Britannica who really tried to convince them to make a sort of more open, web visible encyclopedia, but that didn't work out at the time. Meanwhile, there was another encyclopedia, which was, well, let's see, there were two other things. There was the effort to make a sort of online encyclopedia, a thing called Encarta, which was done by Bill Gates at Microsoft. And they bought, I think, the Funken Wagnalls encyclopedia, if I remember correctly. and tried to make kind of a computerized version of that. And it was an interesting product. Was a commercial failure. And it was I think it was at the time, let's see, it must have had CD-ROMs, must have been right at the time when there was a transition from distributing software on floppy disks to distributing software on CD-ROMs, because you couldn't really have fit the data for an encyclopedia onto floppy disks. That would have been an absurd number of floppy disks. I remember for Encarta, there were things like encoding the images. They were using a very elaborate fractal-based image encoding scheme that I think a chap called Michael Barnsley had been involved in developing, that was based on iterative function systems, and it's kind of a precursor of wavelet-based image compression, but done a different way. But because the goal in Encarta was just like, we got to get some pictures in there, but we got to get them as small as possible to fit on a CD-ROM so that they can actually be used. But that was sort of an early computerized encyclopedia, not a commercial success. I think Jimmy Wales wanted to do sort of a commercial version of that, had Web3 and so on existed, or had Tim Berners-Lee decided that the web should have micropayments from the very beginning, the history of encyclopedias on the web might have been very different from the way it actually turned out. The original kind of commercial version of Jimmy Wales's vision did not work out. And there's a chap, oh my gosh, what's his first name? Sanger, I guess is his last name, and I've certainly met him even fairly recently. Oh my gosh, don't remember his first name. Sorry. Who was kind of more of a philosopher of knowledge type person who was involved in the early sort of conceptualization of Wikipedia. But Wikipedia kind of became this kind of crowdsourced thing. I think it's Jimmy Wales certainly told me that he felt he'd completely lost control of what was happening with it, and wasn't entirely happy with what was happening with it. I do remember this must have been 93, 94 timeframe, going to a conference in Boston called Wikimania, which was, I think, one of the very early, maybe the first kind of, I don't know whether they still exist, Wikipedia conferences. And it was really quite interesting because a lot of people who'd been sort of editing Wikipedia showed up at this conference, and they'd never met each other. And it was a very curious collection of people, because it was a lot of people who were very diverse collection of people in terms of their kind of occupational backgrounds and so on, from some professor types to a lot of sysadmin type people, some librarians, some people who were kind of like, well, I just started editing Wikipedia and it was fun. And it's like they didn't have, they were basically, going from Encyclopedia Britannica and reference books and so on, and entering some of that material into Wikipedia, and using MathWorld actually, which by that time existed as a website, and transferring its material into Wikipedia. I don't know. In modern times, I think most people probably, when I look at Wikipedia pages about people, I figure the person who the page is about wrote this page, because in most cases, I have to say I've avoided reading my own Wikipedia page. I think I'm not as necessary to produce such a page about, because I've written an awful lot of stuff about and said an awful lot of stuff about my own history. And if the world wants to have a decent version of a page about me, there's a ton of material to use to make that. And somehow I think I have been, it's been part of my approach to things to not read stuff other people write about me, because I feel it's not a useful, it's kind of like a video feedback system or something. It's not one of these things where you end up getting, it ends up not being a useful loop. I have to say, I think some of the things, for example, for the NKS book, should be on Wikipedia. I don't know if they actually are, but it's something where for people to take chunks of stuff from the NKS book, where I have pretty good summaries of lots of kinds of ideas, particularly in the notes and so on. I do notice with great regularity that the things that are in Wikipedia are distinctly worse than the things that you could get by just lifting a paragraph and quoting it from the NKS book. But I don't know the processes for getting that to happen. Maybe folks who listen to these live streams could do the world a service and make use of those kinds of things. And I think at some point in the past, we set it up so that a bunch of pictures that we make are usable in Wikipedia in terms of their licenses and so on. And I guess that got some of them to be used, although I don't know how many. I think that this process of having kind of a crowdsourced place, Wikipedia has been very successful in many ways. I think sometimes when you dig into details, it kind of falls apart. But overall, I think it's been a tremendously successful thing. It's always interesting to me to see which of these kinds of crowdsourced things are doable and which are not. I mean, one general rule is if it's been done before, then it can be done again, perhaps better, by kind of a crowdsourced approach. Encyclopedia Britannica already existed, so you could make a kind of online version of that or an amplification of that because there was sort of a pattern for how to do it. I mean, Encyclopedia Britannica as an organization, we've interacted with them repeatedly over the years. It's kind of a sad story because they had quite a large curation effort of people sort of maintaining, a few hundred people maintaining the encyclopedia. And they had a lot of issues because they were printing an encyclopedia and they were, printing a new edition every year and so on. And so there were a lot of issues about, well, wait a minute, if we change that page, it will have a ripple effect that will affect all these subsequent pages. So when we make a change about this thing, we have to make sure that it keeps the same space or doesn't ripple through too many pages. Otherwise, we have to redo 1,000 pages or something in that volume of the encyclopedia. So they had a lot of issues like that. They had also tried to set up an internal database of kind of knowledge, which at various times we interacted with them about using, but I think in the end, it's pretty tiny compared to what we had to build for Wolfram Alpha, for example. And I think but it was sort of an interesting example, I think probably based on Mortimer Adler's kind of ideas about constructs that the way of breaking down knowledge into pieces, I think notions of singulars, things of which there's one of it, versus collective things and so on, things like this, and sort of relationships between objects and so on. And I don't think we ever actually, I don't think I ever actually saw the real sort of pure kind of representation of what Encyclopedia Britannica had. But they had a very state-of-the-art kind of operation going with very good curation, which unfortunately was just not commercially viable after sort of the web and the transition to the web really just didn't work very well. And then Wikipedia came along, and that effort kind of died off. I think it's interesting, as I say, what is accessible to sort of this crowd approach. I mean, for example, one thing we certainly notice is Wikipedia is a great source of kind of folk information, like what are the typical names by which something is known. That's an important thing for us for natural language understanding for Wolfram Alpha. When it comes to sort of raw systematic data that you can compute from, that's a quite different story. Because the crowd, so to speak, will tend to put in a thing. Maybe they'll come from one source originally, and somebody will just copy a bunch of stuff from that source, copyright be damned or whatever. But into Wikipedia. But then they'll gradually, people will say, no, that value, I've got a better version of that. And so gradually, what was something quite systematic will become something that is no longer systematically computable from. And so that's sort of a different objective that one can have. Now, I think it's interesting to see these different kinds of projects that work and don't work. Another one started by a friend of mine named Steve Coast is OpenStreetMap, which was a very successful project. That was Steve Coast actually had been an intern at our company back when he was in high school, I guess, and had then at some point gotten very frustrated. He was based in England. He gotten very frustrated about the Ordnance Survey, Ordnance Survey is the government mapping organization that puts out maps in the UK. And they were like, no, these maps are very proprietary, and you can't sort of openly make use of them on the web and elsewhere. And Steve decided he was just going to launch a kind of a crowdsourced project to just map the world. And tremendously successful project, certainly helped by the fact that GPSs came in and people could start just driving routes and uploading things from GPSs and annotating maps and so on. And it's been, I think it also helps that in a geographic setting, there are, somebody can decide, I really want to see the maps be right for Costa Rica. And, I'm going to make, really put an effort into making that happen and become the sort of person in charge of that kind of mapping. I know in that particular case, I ran into the person who was in that particular role, who had been, I think, working for the Postal Service in Costa Rica, where they had tremendous trouble from streets badly named and misnamed and renamed and so on, and had just decided, use the OpenStreetMap framework and just get the thing straightened out. And I can't speak to the precise quality of what was done there, but that was sort of a general kind of impression of what was going on. But that's a place where maps had existed, obviously, but this was a place where one could take sort of the crowd and in that case kind of organize it in some cases rather regionally to produce a high quality sort of street map of the world. I think this whole question of sort of what happens to these communities, and particularly the originators of these communities, how are they, at what point do they sort of lose control of the collective creature that they've produced? And the answer is, I think, fairly early. The versions of this that are successful, that usually happens. And it's actually a very, if you were to say, is it a good career move to start one of these things if you want to feel satisfied in the end? Well, it's good if you are satisfied by the fact that the thing you launched becomes a big thing in the world. It's very unsatisfying if you care about the thing you launched operating in ways that you thought it should operate, or that the people who are operating it kind of think more of you than just that it's the sort of originating guru, so to speak. It's one of these things where people say, well, it's a sort of cautionary tale in terms of crowdsourcing kinds of things. But that's what I know about that, I think. Let's see. Somebody's reminding me it's Larry Sanger. Apologies, Larry. I know Larry has been interested in some blockchain-related encyclopedia projects, and we've interacted about those kinds of things. I think, I will say, by the way, that there is a lot of opportunity for other ways of communicating knowledge and sort of encyclopedic knowledge. One of the things I've long wanted to do is to take our sort of computational essay kind of format and produce a kind of an exposition project, just expositions about all kinds of things in a mixture of human language and computational language, so that one is not only just reading the narrative, but also able to actually compute from the things that are written on the page. And I've done that to a certain extent. And certainly one of the things I've taken as a principle for the last few years in writing things about science and so on, is that every picture in every piece that I write, you should be able to click on it and get the Wolfram language code that you can run anywhere to compute with. I have to say that I feel like what we've got in Wolfram language and our sort of effort to make a computational language that can describe everything computationally, I think it is finally a good way of making raw material for sort of representing knowledge computationally. And I feel pretty good about the fact that I can pick up kind of pieces of open language code from 35 years ago and run them today. That's a good sign that we didn't make compromises that are kind of going to, over that span of time, we've dealt with a lot of change in kind of the world of computing, and yet the kind of the principles there and the actual code still runs, and I think we can expect that to continue into the sort of infinite future, because it's one of these cases where what I defined was a language which was defined for its own sake, not a language which was defined for the purpose of fitting into the particulars of the computer hardware of 1987 or something. And so that's something which, like mathematics, like sort of formal kinds of systems, is something which is timeless. And so you can expect can be preserved and can keep running into the future. We haven't ever had that before. We've had, in the 1600s, people talked about sort of philosophical languages as a way to represent knowledge independent of human languages. That was a thing. Leibniz, John Wilkins, people like that wrote about this. But they didn't have the material. They didn't have computers. They didn't have the internet, the web, ways to communicate knowledge, things like this, which we have today. And finally, I think we have, well, after the 40 years I put into it, we have kind of a language for representing knowledge computationally. And I think there's a sort of a great opportunity to build sort of the next level of encyclopedia-like thing as something which is represented in computational language. It's very important that you actually have a computational language. It's not going to work if you're writing things with programming language, because programming language doesn't have a representation of a city or even a graph or an image. Those are things not part of the programming language as such, but they're things you need as the raw material to sort of talk about things computationally if you want to get far in talking about them. So I think we sort of have a unique opportunity now to sort of build the next level of these kinds of things. And I've been sort of trying to kind of define how to get that started for a while. And it's one of those projects which is a project one would like to see done, but it's a challenge to do. I think, we started something like that with our demonstrations project back in the mid-2000s. It's been quite successful. Now, I don't know, 13,000 or so of these runnable demonstrations, in notebooks and on the web, of all kinds of things. Demonstrations are more for their sort of visual effect, and run the slider and see this and understand how some particular thing works, more so than for the code inside them, which basically at this point is like, if the code works and produces the thing you want, that's great. But I think what's important about computational essays is the use of code, the use of computational language as an actual piece of exposition, just like mathematical formulas can be used as a sort of piece of exposition. That's an opportunity to do that. And that's sort of a new possibility that exists today, is sort of different from the kind of thing you find in the traditional encyclopedia to Wikipedia type thing, which is more of a narrative where which is intended for people to just read, as opposed to something where you can expect to build on it explicitly, rather than just have it go into your brain and then you learn from it. All right, I should wrap up soon here. There's some comments. Alistair's commenting that HP 9800s were awesome. Okay, they had overlapping video memories. One was ASCII character based, the other was HP plotter language controlled. Wow, I think that the pen plotter output desktop calculator thingy that I used was a 9 something or other HP device, but it didn't have that same. It didn't have the only display it had was oh my gosh, what are those? It was beyond there were 7 segment displays which are made from light emitting diodes from an array of sort of light emitting diodes in the shape of an 8. But then there were fancier versions of that that could display sort of lots of characters as these kind of miniature bitmap displays, just sort of a ticker tape, one character at a time. And I think that's the kind of thing that had, along with probably a thermal printer that printed a little strip of paper. Actually, that's a good question, whether I still have programs. I must still have programs that I wrote on that machine. I did a bunch of physics calculations on that machine, and I was kind of using, at the time, I was using that machine and a mainframe computer that was programmed with cards. And I'm trying to remember whether there was any way of getting graphical output from the mainframe at that time. Not sure that there was. Soon thereafter, there was a company called Printronix that made dot matrix printers. And a dot matrix printer has a line printer, which was kind of the typical output device of a mainframe computer, was something which had this kind of belt that went around that had all of these sort of little things like like printing font characters. They had little like typewriter keys, but on this belt, and it would go around, and it would how did that actually work? It would print a line at a time using that, and I'm now forgetting quite how that worked. But sort of the next technology was the dot matrix printer, where there were which was an array of dots that would be printed across the page. And with those, where the characters were formed from collections of dots. And in those allowed some sort of primitive graphics to be produced. I remember there used to be, even in early Unixes, there was a program that was kind of part of the operating system, I think, that provided some basic graphical output on things like Printronix printers. Back in those days, it was sort of a big deal that you had to have a separate driver for every different kind of printer and so on, because they all accepted their data in different ways on serial interfaces, on parallel interfaces, et cetera, et cetera, et cetera. It's only later that all these standards for representing these things got established. I mean, you know, it's kind of remarkable to me today that in VR, for example, virtual reality, it is bizarre that, to my knowledge, there isn't really a standard that's emerged for how do you represent all this 3D imagery. I mean, there are things like Unity and Unreal and so on, which are essentially game engines that people use, but it's kind of crazy to be representing what is really just 3D imagery using a whole game engine sort of code-based system. But for some reason, and this reminds one greatly of sort of the early days of printable graphics, that there weren't those kinds of standards. I think laser printers became a thing. I first got a laser printer. It's made by a company called Imogen, I remember. I must have gotten that laser printer in 1984. And it was a great big object that was probably fairly expensive. Yeah, no, let's see, that's right. And there had been previous things, the same kind of technology that were used, for example, to print the kinds of things that you were going to use to photographically make the masks for integrated circuits. And I think there was a company, Versatech, I think, that made printers that printed those things out on very, very wide paper. I was just reminded of this just yesterday as I was digging through the history of the NKS book, because I remember back in 1984 or so, printing out a giant picture of Rule 30, 2,000 generations of Rule 30, which at the time, no, I think it was that, on this giant roll of paper, printed on one of these printers that was intended for printing out what would turn into masks for an integrated circuit. Well, perhaps for circuit boards, but I think for integrated circuits. In any case, it was a high resolution printout on some kind of photographic paper. Actually, those early laser printers always did that, and they had so I'm not sure exactly how, but it was not on sort of ordinary paper. But in any case, that printout had the interesting sort of history that it was, high resolution printout of Rule 30. So I got to see, what does Rule 30 do? My sort of cellular automaton that produces complicated behavior from a very simple rule. And I remember having that printout on the floor at this company, Thinking Machines Corporation, that made parallel computers and was actually used to generate the bits that were sent to the printer to produce this picture. And Dick Feynman and I were both consultants to that company. And Dick Feynman was very interested in this Rule 30 phenomenon. And he had this argument for why a particular line in this image would be exactly slope 1/4. And so we were kind of going around on the floor with these meter rules trying to measure this thing on this picture. In fact, it turns out it's not exactly 0.25 slope, it's like 0.2481 or something like that. But in any case, so that particular piece of paper, or at least a copy of it, made, I think probably that particular one, I laminated years ago, and I still have it. And it's this big roll of big roll of stuff, and it rolls up very nicely. And I was just remembering that my children, when they were quite young, it's this big rolled up thing, and so you can go inside it, and it's as tall as probably up to a 3-year-old or something, or a little bit more. And it was a source of great entertainment to sort of go inside this giant rolled object, and so it found this Rule 30 printout found a good home. I was just reminded of this yesterday because I was writing about the way that graphics were produced, the NKS book, which was sort of a subsequent generation of these kinds of things. All right, I think that I need to wrap up here. It looks like it's time for my next responsibility in my day job, which I think is also a live stream, looking at, having talked a bit about history here, now I get to build a little bit of the future, put another few bricks into the cathedral we've been building these last 4 decades or so. And I think if I remember correctly, it's a review about visualization. So it might be the little bit of the future of some of the questions that were asked here about computer graphics, I hope. So thanks for joining me, and see you